Hello, my name is Ellen Helm. I am the Energy Services Portfolio Director at Trane, and I lead our national lighting team. This video is titled HVAC Integration. It is part of the ESTCP Advanced Lighting Controls Technology Transfer video series. This video is an overview of the integration of lighting controls and HVAC controls. Within this module, we will define HVAC integration and the benefits it provides. We will cover best practices and future trends. We will conclude with an example of a Department of Energy project that integrated these control systems in 5 commercial buildings. Lighting and HVAC account for more than 50% of commercial building energy consumption. To obtain maximum energy efficiency, light should be dimmed, and HVAC set points should be adjusted when a space is not being used. Since lighting is everywhere, luminaire level controls in the lighting can be leveraged to not only dim the lights, but also control the HVAC temperature set points when occupants leave a room. Integrating lighting and HVAC also gives a facility visibility and the ability to control the 2 largest energy consumers. It is not uncommon today for a building to have multiple control systems for lighting and HVAC, sometimes even multiple systems for each. In its simplest form, the integration of lighting and HVAC provides the ability to control lighting and HVAC from shared occupancy sensors. With a single point of control for both systems, shared schedules can be implemented, providing synchronized behavior of the light and temperature levels based on predetermined scenes as well as occupancy status. Energy usage for both systems can be aggregated and analyzed from one convenient dashboard, and energy conservation decisions can be made for both systems concurrently, ensuring maximum user comfort and safety. For example, in the case of a demand response situation, light levels can be dimmed along with raising HVAC temperature set points for cooling. This can minimize the discomfort that can occur when only HVAC is considered, with really very little effect on lighting performance. Integrated controls is the last step in a progression of energy conservation measures that can be implemented with lighting and lighting control upgrades. The first step is to install quality, energy-efficient LED lighting with the capability for control. Next is the incorporation of advanced lighting control strategies such as task tuning, daylighting, and occupancy sensing, as discussed in a previous module. These energy-saving strategies are available with network lighting. Once the lighting is networked, savings can also be extended to plug loads and HVAC systems. Finally, to achieve the deepest energy savings, this network lighting system can communicate digitally with building automation systems via the BACnet protocol to allow for a broad variety of HVAC efficiency measures. Thermostat setbacks are the most utilized strategy for HVAC systems. When the occupancy signals from the lighting system indicate an unoccupied status, during an occupied mode, the active heating-cooling set points are set back by typically 3 to 4 degrees. In the case of variable air volume, known as VAV systems, additional strategies can be incorporated pursuant to ASHRAE Guideline 36 to control airflow. VAV box turndown or shutoff reduces or shuts down airflow when an unoccupied signal persists for 5 minutes. Similarly, an AHU RTU supply fan can be set to a minimum speed or shut down in the case of an unanticipated, unoccupied status. Ventilation reset controls as well as demand control ventilation allow for the recalculation of required fresh air per ASHRAE 62.1 and control of the outside air damper position based on the number of zones that are unoccupied. The benefits of integrating the lighting and HVAC systems extends beyond deep energy savings. Current control of buildings can be cumbersome with multiple lighting and building automation systems, each operating from their own control platform. Integrating these systems enables analysis and control from one user interface. Failure conditions can be easily assessed remotely from a central office or even from a facility manager's mobile device. This single interface can also allow for the intelligent analysis of energy usage over time and ultimately result in better decisions regarding space utilization. With lighting and HVAC accounting for more than 50% of a building's energy consumption, integrating the two systems provides for sensible energy control, especially in the case of a demand response request. With integrated systems, we are able to combine a reduction in light levels with the reduction in heating or cooling measures taken by the HVAC system to maximize the comfort of the occupants while achieving the desired energy reduction. Finally, once a networked and integrated system is designed and installed, it can easily be scaled to incorporate additional lighting systems, plug loads, or window shades as expansion opportunities require. These systems easily adapt to changes in building use and can be revamped without costly rewiring with a relatively simple rezoning activity. While full lighting and HVAC integration is often the desired outcome, financial and project time constraints often require a phased approach. It is critical to start with an LED solution that has control capabilities. Number 1, the most basic form of control is standalone control, which involves basic automatic on-off switching of a lighting load on a switched leg. The signal can be provided from an occupancy sensor or a light sensor or another building system. This is a basic energy savings measure employed in many buildings today. While simplistic and effective, the standalone approach is limited in functionality. The second approach, standalone room-based control, is designed to offer plug-and-play installation with out-of-the-box energy code compliance. This approach utilizes a load controller to provide control of a group of luminaires and the benefit of some pre-configured lighting sequences. The third step in the path to integration is to incorporate networked lighting controls. In this type of design, lighting controllers have unique addresses within the lighting network. Lighting loads can be zoned and rezoned for optimal flexibility and are not limited to switch legs and the electrical wiring. Several controls manufacturers provide the ability to upgrade from a standalone approach to a networked lighting controls approach. A variety of control strategies become available as have been discussed in previous training modules. Finally, the fourth step, integration of the lighting and HVAC through the building management system, provides the ability to exchange information between these two energy-consuming functions and provide more complex control scenarios, as were discussed in the prior two slides. Several network lighting systems have the ability to integrate to a building automation system through BACnet protocol or the use of a custom application known as Application Programming Interface or an API. Advanced planning allows for today's standalone room-based control scenario to be upgraded later to a network lighting control system or even integrated to include real-time monitoring and control of both lighting and HVAC systems. Now I'll turn it over to Scott Shooter to present the remainder of this video.
Thanks, Ellen. My name is Scott Shooter. I'm a principal engineer at Slipstream. HVAC integration can be challenging and needs a lot of thought put into it. The following slides provide a few best practices that will help with these challenges. HVAC integration projects require several individuals to divide ownership of a large number of tasks. This division of labor requires some forethought. This figure describes team members' roles that are necessary for successful implementation. One individual, like the electrical contractor, may cover multiple roles. The integration manager role is critical and should not be overlooked. Successful integration of different building systems will entail some challenges, and someone will need to be accountable for problem solving and team coordination. The integration manager could be capable of performing the programming tasks necessary to tie systems together, but regardless needs to oversee and coordinate the programming work done by other members of the team. The integration manager role could be filled by the facilities manager, an energy consultant, a lighting professional, or any other roles identified here. The important thing is making sure someone is accountable for this coordination role. The typical HVAC integration project proceeds through planning, design, and then construction phases. In the planning phase, an economic assessment helps determine the viability of the project by comparing it against alternatives. For HVAC integration projects, a lifecycle cost analysis may be a better representation of the project's value, as opposed to a simple payback analysis. A preliminary planning exercise can reduce challenges later in the process. Planning should include ensuring compatibility for systems integration and evaluating existing controls. Cybersecurity, covered in more depth in a subsequent video, is an important part of any HVAC integration project. Bringing the facility's IT staff into the project early will mitigate issues down the road. The design phase of the project includes elements surrounding lighting controls, network design, and HVAC control integration. The construction phase includes the installation and configuration of the controls. The network is set up and the HVAC controls are programmed. Finally, facility operators and occupants are trained on the functionality of the new system. Note that more detail is provided on subsequent slides and in the guide referenced on the last slide of this presentation. In the lighting and controls design step, attention should be paid to the coordination of HVAC and lighting zones. HVAC zones are largely driven by existing HVAC system design and thermostat or terminal unit locations. Lighting control zones are based on luminaire and lighting control locations, as well as space usage needs. The coordination goal is to align lighting zones with existing HVAC control zones as best as possible. Zone matching does not have to be a one-for-one relationship. Multiple lighting control zones within a single larger HVAC zone would be certainly common in many instances. Within the design phase, some additional effort is needed to plan networking components and configuration. Whether the majority of the lighting control system is wireless or wired, some wired networking will be necessary for the integration. The electrical contractor takes the lead on this, with help from the manufacturer's sales rep. The networks can be very simple, but some forethought is still needed. Considerations include how many networks are needed, the creation of a network diagram for documentation purposes, and whether the system will connect to a local IT network. During integration, facility IT staff, the lighting control commissioning technician, and the HVAC control contractor or technician will need to work closely together to discuss and resolve network integration issues. Once the HVAC system is receiving the appropriate BACnet objects representing zone occupancy, the HVAC technician should be able to revise existing sequences to reflect the design intent. After the custom HVAC control programming is implemented, commissioning will ensure the system is operating correctly. HVAC integration is currently a complicated process, but manufacturers and integrators are making strides in simplifying every step. However, the upfront investment remains challenging. HVAC integration is most easily justified on large buildings with variable occupancy. Capturing additional non-energy benefits will improve economics through value stacking. Ellen previously alluded to asset tracking and space utilization. Additional value can be gained through future integrations with other systems such as security systems. Finally, participating in utility demand response to our load-shedding programs can bring in additional revenue. On a recent Department of Energy-funded project, Slipstream worked with key partners to successfully demonstrate HVAC integration of the Cree SmartCast lighting system in 5 commercial buildings in Minnesota. The objectives of this project were to inspire the retrofit market to go beyond simple lighting fixture retrofits. A part of this was to demonstrate the energy savings and barriers at each site. Xcel Energy designed a utility program as part of the overall project. This effort helped market actors get further up the learning curve, supporting broader adoption. The 5 sites were all in the Twin Cities area and included office, education, mixed use, vehicle service, and outpatient clinic areas. The HVAC systems that were integrated included variable air volume systems with hot water and chilled water plants, a dual duct constant air volume system, and packaged rooftop units. Integration was successful and saved energy at the 3 VAV sites. The average electricity savings across these 3 sites was 3.8 kilowatt hours per square foot. Natural gas savings averaged at 5.6 kilobtus per square foot. Applying utility rates to the energy savings resulted in utility bills savings of 45 cents per square foot. Simple paybacks were calculated using capital costs and utility incentives and averaged to approximately 7 years. The site with single-zone rooftop units had negligible savings due to poor zoning. Integration was not completed at the 5th site, unfortunately. Slipstream has produced several resources to help practitioners implement HVAC integration projects. One is an implementation guide which goes into more depth on many of the topics discussed in this module. Another is a savings estimator that gives reasonable project-specific energy savings and economic estimates. This brings us to the end of this video. Thanks for watching.